Alright, now we will look at the cross product for vectors. And we write that as A cross B. And this time the result is a vector, whereas, if you remember, A dot B was a real number. And remember, that's dot, that's not multiplication. So we're going to just do this in the three-dimensional case. So we need a definition. And the definition is determinant of a 3 by 3. And the way we work that is, let's try A, B, C. Now you might remember what a determinant is if you've talked about matrices in the past. And it's represented by two straight lines, looks like absolute value, but the determinant, it's going to be, the way that we're going to figure it out is we're going to cross out, we're going to use A, the first entry, then we're going to cross it out, and you take the determinant of what's left, and then we're going to minus, we're going to move to the second column, B. So first we use A, now we're going to use B, and we're going to cross B out, and what's left is D, F, G, I. We're going to get determinants of 2 by 2s, and then we're going to move on to C with a plus. Notice the signs alternate, it's plus, minus, plus, and then cross out the C, and then we're left with D, E, G, H. So if we cross out A, we're left with this. If we cross out B, we're left with these two columns, and when we cross out C, we're left with this. And that's how we're going to do our determinant. Now, how do you do a determinant of a 2 by 2? Well, if you just have A, B, C, D, those are easy. You just cross multiply AD minus BC. Now, if we use the unit vectors I, J, K, and if A is a vector A, B, C, and B is the vector D, E, F, then A cross B, we're going to work it as I, J, K, A, B, C, D, E, F. Now remember, the determinant of a 3 by 3 is we're going to take I, we're going to cross it out, we're left with the determinant B, C, E, F. Minus J, okay, we cross that out, we're left with A, D, C, F, plus K, we cross it out, we're left with this, A, B, D, E. Okay, so we have I, this is going to be B, F, minus C, E. Now you don't have to memorize this, you just have to learn how to work them. A, F, because in the next section we're going to use it a lot, minus CD plus K times A, E minus B, D. And that's going to give us the cross product of two vectors. So let's do a specific example. I think this calls for one. Suppose A is a vector 4, 3, negative 1, and B is the vector negative 5, 0, 2, and we want to do A cross B. So to set that up, you're going to use I, J, K. Remember, those are the unit vectors in the direction of the X, Y, and Z axis, respectively. And we just put A in the second row and B in the third row. Okay, starting with crossing I out, we're left with 3, negative 1, 0, 2. It's always minus J. Crossing the J column out, we're left with those. And then crossing the K column out, we're left with that. Okay, this is going to be 6 minus 0. This is going to be 8, and that's going to be 5, minus 5, and that's going to be 0, minus a negative 15, and that's going to be 6i minus 3j plus 15k, and we get the vector 6, negative 3, 15. So remember, this shows us that the cross product is a vector in itself. Now it has a lot of properties, so I'm just going to go through them. They're easy to prove, so I'm not going to prove any of them, but they're really easy to prove just using the definition that I just gave you. First one is that if you cross a vector with itself as 0, the magnitude of A cross B, it's almost like the magnitude of A dot B, but it's going to be using sine theta instead of cosine theta. A cross B equals 0 if and only if A and B are parallel. That's an important one. If you do A cross B, then you can't really reverse the order. That's going to be minus B cross A. You're going to have to add a negative if you reverse the order. If K is a scalar and you cross it with B, then that's the same as doing K times A cross B, or it's the same as just crossing A with the scalar times B. So K is a scalar. That means it's just any real number. If you want to cross A with a B plus C2 addition vectors, you can use the distributive property. And if you do it on the other side, it's still going to be A cross C. That's distributive. Also, you just have to watch your order of the vectors. If you combine this with the dot product, it's the same as just dotting A with B cross C. And if you do A cross B cross C, you get A dot C times B minus A dot B times C. It can be shown that, and this is important, that the magnitude of A cross B is equal to the area of the parallelogram with sides A and B. So that's one application of it. Another one is that if you do A dot B cross C, and we can show that that is just A1, the determinant of A, B, and C put in a matrix. That's not hard to show. The book shows that. And that's the volume of a parallelepiped. That's a three-dimensional box, but it doesn't have to be perpendicular or parallel. The sides don't have to be perpendicular or parallel. Determined by A, B, and C. And then finally, another application is torque. And that's the tendency to rotate about the origin. That's like if you tighten a bolt, you're rotating it around the bolt so you can measure the torque. And that's the best picture you can think of. So you have, if you think about it, you're going to consider a force acting on a rigid object. So the rigid object would be the bolt, and the force would be what the wrench is doing to the bolt. At a point given by position vector r. So, I mean, if we have, let's just do like 2 space. Here's your point. Then the position vector would be r. Then the torque is r cross f. It's your position vector crossed with the force. And also, you could say that that is the magnitude of r cross f, which in a property we said that that was the magnitude of r times the magnitude of f times sine theta, the angle between the two vectors. Okay, well, look at the sample homework problems. I've done some of the homework there if you want some examples.